Hola, hi, this is Al, your statistics instructor. Let's get to work. So, in this video, we are going to try to answer two questions. One, what is the periodogram? And two, why is the periodogram useful? Okay, so those are the two questions that we're going to answer in this video. So, first, allow me to remind you about the definition of the spectral density. Okay. So remember last time during our last, during Friday's lecture, what we did is we presented the definition of the spectral density or spectrum. Okay. So it was given by this. Okay. It was summation k goes from negative infinity to infinity of the autocovariance function times e to the negative 2 pi wi, where I is the square root of negative 1, times k. K represents the lag. So then we broke down that series that went from k equals negative infinity to infinity into these three components, and then using this identity, we rewrote it like this. Using Euler's formula, we were able to rewrite the sum of these two exponentials as 2 times cosine of a particular w, a particular frequency. Okay, so this is an alternative formula to compute, to find the spectral density of a time series. Okay? Okay, now let's talk about the periodogram. Don't forget this expression here. Gamma at 0 plus 2 times summation k goes from 1 to infinity. Gamma at k, the autocovariance function, times cosine of 2 pi k times w. K represents a lag, w a frequency. Can you see that the periodogram is just a sample version of the spectral density? Okay, so that c hat is just an estimate of gamma, okay, the autocovariance function. That's it. And since we have n, since our time series is of size n, right, we have n observations, then it can't go up to infinity. Okay, so we have to stop here. So bottom line, the periodogram is just a sample version of the spectral density. Okay. Now, next, so we have already answered what the periodogram is, but why is this useful? Why is this function useful? So let me go to the next slide, and what we're going to see is that if you make a graph of w against this, against the f hats, okay, if you make that graph, you're going to be able to identify important periodicities present in your time series. Okay, that's why this guy, the periodogram, is useful. It's going to be very useful to identify periodicities present in your data. Okay, so let me illustrate this idea using R. So the first thing that we're going to do is we are going to create a very simple time series, one that has cycles, one that shows seasonal behavior. Okay, so let me launch R. Now, let me go to the next slide so we can copy paste this. Again, these lines of code are going to be producing a very simple periodic time series, purely periodic. In this case, we don't have a noise term. You'll see it in a sec. So first, n, the sample size, is going to be 200. Okay, then we're going to produce a sequence using R with this command, one that goes from 1 to 200, 1, 2, 3, so on, up to 200. Then these x's are going to represent the almost the frequencies. Okay, so in this case, for instance, the first one, it's going to be 2 pi times 1 over 10. Okay, the next one is going to be 2 pi times 2 over 10, and so on. And then we're going to add a 2.5, apply the cosine function, multiply it by 4, and then finally add a 5. You'll see that we're going to end up with time series that shows cycles. And as you can see from here, from what we did here, the important frequency will be this guy, so 1 over 10. So let me show you this. So as you can see, right, we have that pattern that is repeating itself. Okay, and this is purely periodic. We don't have noise. Okay. Okay. So what we're going to be doing next is trying to find the periodogram, the sample version of the spectral density function, okay, for that time series. So how can we find the periodogram using R? Let me show you on the next slide. We have the command that we need, spec.pgram. Okay, that is going to help you find the periodogram. Okay, so that function from R allows you to calculate the periodogram using the fast Fourier transform, and you could produce a smoothed version of the periodogram. In this case, we don't want to use the fast Fourier transform, and we want to produce the raw periodogram. Okay, so in order to create that raw periodogram that we want, I need you to set these two options, these two arguments for spec.pgram equal to false in the case of fast. That has to do with the way that it is computed. We don't want to use the fast Fourier transform here, and taper equals 0. Okay. Again, these options allow you to create the raw periodogram, not a smoothed version of the periodogram. So let me copy paste that. So can you see that? First, let me try to describe what we have here. So going back to the time series that we created, so we have this cosine function. We know that those cosines well, that cosine function, it's going to repeat itself after a cycle of 2 pi, right? And also using properties of the cosine, we know that, for instance, cosine of an angle alpha equals the cosine of alpha equals cosine of negative alpha. So you don't necessarily need all the values for the entire 2 pi cycle. Okay. Another thing that you know is, for instance, that cosine of alpha plus 2 divided by pi, right? So that would be the same as cosine, well, would be the same as negative cosine of alpha. Okay, so bottom line, what I'm trying to say here is that you could take advantage of the properties of these trigonometric functions, and you don't need to talk about this for the entire 2 pi cycle. Okay, so what you're going to be seeing here in R is that what you get is just from 0 to half of that cycle. Again, so an entire cycle would go from 0 to 2 pi, and what you're seeing here are just the W's, if you will, the x's. Okay, so you're not going to have everything from 0 to 1, but just from 0 to 0.5. Okay, makes sense? Now, just from our example, what you have here, the important frequency is going to be 1 over 10, okay? Because that's the cosine that is driving the behavior of this function. And the periodogram is able to identify that important frequency. Make sense? Okay. So that's why this guy is useful. As advertised, this guy, the periodogram, is going to be able to identify important frequencies. Okay. So now the thing is, this function that we have here, the one that we created, let me redo that graph. It doesn't contain a noise term. So what we're wondering now is it possible to do something like this for a time series that contains an error term? Is going to be the periodogram able to identify the important frequency, the one that defines the underlying cyclic function that models the behavior of your time series? So to find out, again, we're going to be using R. What we're going to be doing is now creating a noisy version of this function y that we have here. Okay, so here we go. So this is the noisy version that we have. It's the same as what we had before for y, but now we're going to be adding Gaussian white noise, mean 0, and the standard deviation is going to be 0.25. Okay, so remember that R norm is a function from R that allows you to produce pseudo random numbers. In this case, we're going to be producing 200 of them. We're going to be generating 200 of them, mean 0, and remember that the R norm function uses the standard deviation as its parameter. Okay, so once we have created that error term that Gaussian noise, Gaussian white noise, then we're going to add it to the underlying cyclic component of our time series, okay? And then we're going to be creating this new time series that contains an error term with just adding the Gaussian white noise to the original y, okay? So let's do that, and then we're going to make a plot. So this is what it looks like. So it's not too bad. The thing is, but the thing is that now this guy has a noise term, okay? It is not as regular as the other one that we had before, right? Okay, so now let's find out if the periodogram is able to capture, to identify that important frequency. Remember that the important frequency, the W that we would like to be able to catch, is 1/10. In this case, we know that that's the important one, so that's why we're doing it with simulation, so we know if the periodogram is able to do its job. Okay. So again, just like before, let's use the spec.pgram function. Now we're going to apply it to that noisy version. And remember, we want just the raw periodogram, and to do that, set the fast argument equal to false and the taper parameter equal to 0. So let me do this, copy paste. And yeah, the periodogram doesn't look as smooth as it looked before, right? We have some jagged version here, have a few spikes, but then the most important part is this. Remember that here on the horizontal axis you have your W's, your frequencies, and here the vertical axis is your f hat W, your estimate of the spectral density, and still we were able to capture the important frequency, W equals 0.1, okay? So, just to summarize what we did here together. So, what we saw is that the periodogram is just the sample version of the spectral density of a time series. And with this graph that we have here that presents on the horizontal the frequencies, and remember that R will be doing this just for half the period. So in this case, instead of going from 0 to pi, from 0 to 2 pi, is going to go just from 0 to 0.5. Okay, and these guys represent the frequencies, the W's. In this case, the important frequency was 1/10 times 2 pi, right? Again. So the thing is, we were able to identify that important frequency here. The spike here is telling you that 0.1 is the important underlying frequency in your time series. And that's why the periodogram is useful, because it allows you to identify those periodicities present in your time series. So this approach is going to help us model seasonal data. Make sense? Okay, so that's it for now. See you on the next one. Take care. Bye.